So folks, we've got quite a journey ahead of us for solving these nth order linear equations. And we're going to learn quite a few different techniques, but I want to give you a general outline for how we're going to be solving these equations. And don't worry about some of this just yet, but as we go further along, return to this outline and see how we're meeting the steps of it. So the first thing we need to do is we need to solve what's called the corresponding homogeneous equation. So what do I mean by that? Let's suppose that you were asked to solve the second order equation y double prime plus 6xy prime plus sine of x y, and that equals x squared. So if you were to solve this second order linear ODE, the first thing you would do is you would solve the corresponding homogeneous equation. So the first thing you would do is you'd solve y double prime plus 6xy prime plus the sine of x y equals 0. So this is the corresponding homogeneous equation, and we'd want to find a solution to it, or find the family of solutions to it. The next thing we're going to do is we're going to find one particular solution. That is, we find one solution that solves this ODE up here, and then we combine the two solutions together to give our general solution to the ODE. We'll talk more about this as we go along, but I just wanted to give you kind of a heads up for that. And what we're going to focus in on is right now are for techniques for solving the homogeneous, for solving these if they are homogeneous. And then we will elaborate on our techniques as we go along. So what I'm about to show you is the technique of constructing a characteristic equation for this, in this case, second order ODE. And this characteristic equation technique is only going to apply to nth order linear ODEs, but here we require that they have constant coefficients. So really we're very much narrowing our focus here. In this case, we've got a homogeneous second order ODE with constant coefficients, and I want to talk about what the solutions to that might look like. So here we go. What we've seen a number of times before is that when we solve ODEs, a lot of times they have both y and y's derivatives, and they need to cancel out in such a way to give us some expression. And so our candidates for solutions are often functions that have e to the x in them, or sine of x, or cosine of x. Those are the functions, some of the functions whose derivatives start to repeat themselves, and we could then expect some of the appropriate cancellation to occur. So let me just show you this trick. What we're going to do is we're going to guess that y equals e to the rt solves this ODE. And we've seen this a few times where we sort of start with a guessed solution. Now we'll have some more work to do later on, and we won't actually get into that in this video. But we start with a guessed solution, and then we go ahead and figure out what criteria that guessed solution has to meet. So if we were to take the first derivative of this, we get y prime is equal to re to the rt. And if we were to take the second derivative of this, we get y double prime is equal to r squared e to the rt. Then let's go ahead and plug each of these three functions into our original second order homogeneous ODE with these constant coefficients. And so what we'd have is a r squared e to the rt plus b times re to the rt plus c e to the rt needs to equal 0 for this to be true. And again, remember what we did is we started by saying let's suppose e to the rt solves this ODE. Okay. Well, notice that all three of these terms have a common factor of e to the rt, so let's pull them out. So that's going to leave me with a r squared plus br plus c e to the rt needs to equal 0. And just be careful here. We've got two factors. We've got this factor here and this factor here, and they're being multiplied together to equal 0. So by the zero product property, either e to the rt equals 0, but what? That never happens because there's no number I could plug in for t to make that output a 0. Or then the quadratic equation, ar squared plus BR plus C must equal 0. And this is what we're going to call the characteristic equation. So that's our characteristic equation. So if R is a root of the characteristic equation, then y of t equals e to the RT solves the ODE. Now, there's quite a bit more to this than what I've said so far. One of the things that we need to talk about is, typically, I shouldn't say typically, but oftentimes we find that the quadratic equations have two roots, but they don't always have two roots. Sometimes they just have a single real root, and sometimes they have complex roots, and we're going to have to see what we're going to do in each one of those cases. And the other thing we haven't talked about is whether or not we can guarantee that our solution is a general solution, or whether the solutions that we find using this method will help us reach any solution to this ODE. So we still have some more work to do, but that's our general strategy for these nth order linear ODEs with constant coefficients. It has to do with solving the characteristic equation, finding the roots of the characteristic equation, and then learning how to deal with the special circumstances that it might arise when we have either complex or repeated roots.